Well, I would like to thank Anatoly and Alekos and Catherine for the invitation. And like Anatoly, I perhaps have to say some words, let's call it of apology, because I'm working in ergodic theory, topological dynamics, and I don't think I knew anything about model theory until about, a decade ago or something like that. But since then, I keep running into model theory nonstop. Whatever I do is either influenced by model theory or has some influence on it. And let me just tell you quickly what this story is from my point of view. So Benji Weiss and I worked on dynamical systems. I mean, of course, classical dynamical system started with real actions, integers maybe. And then they were generalized eventually to locally compact groups. And in this setup, Alice already showed that there is always, whenever you have a topological group, then there is a universal minimal dynamical systems. We heard about it a lot. And it's never, so G locally compact, second countable, say, and of course non-compact. Then it's never metrizable. But then we were looking at other groups. So what comes next? Polish groups. And maybe the easiest one to work with naturally is S infinity. So all permutations, a Polish group. And so we started to investigate this group from the point of view of classical topological dynamics, Alice theory, etc. And we were in connection with Vladimir Pestov about that. I went to visit him in New Zealand. We talked about it. And when I came back, we couldn't solve the problem there. But when I came back, I worked on it further. And I worked with Benji. And we discovered that this space, LO, linear orders on the integers, say, is this object, surprisingly, the same thing as MG for G S infinity. And we all, moreover, discovered that this has what we call a fat orbit, so dense G delta orbit, and there is a unique invariant measure, probability, which is supported on that unique on that fat orbit, and this was the first step. Later on, we went over to another group. We looked at the homeomorphisms of the Cantor set, and here again we discovered that one can actually give a concrete description to this universal object. And well, that's because we didn't consider that as a part of model theory. We didn't think about going further. But then came this seminal paper of Kekris, Pestov, and Bolshevich, which again we hear about again and again in this conference. So this was kind of direction from topological dynamics to model theory. And moreover, this part where there is a fat orbit was taken more seriously, let's say, or put into the context of model theory by Kekris and Rosendahl. They were talking about ample dynamics, etc. And finally, along this vein, here a more recent paper by Kekris, Lyons, and Angels, treated the question of when. I was considering that question for a long time. I mean, after I realized that, after we knew that there is a uniquely ergodic measure here, unique ergodic measure here, and after I was more familiar with that paper, I asked myself the question whether which groups preserve this measure uniquely. But I couldn't solve it. I didn't have the model theoretical tools. And I gave it to a student. He worked on that. He had some but this was beautifully solved here and with many variations. Okay, so this was perhaps the first encounter with the model theory, and then another one came in this way. This also was mentioned here. There was this work of Ouspensky, where he showed that this group is Rilke precompact. And I read his work, and it occurred to me that I can prove in a very similar way that this group, this is the unitary group. Is Rilke precompact. Automorphism of mu. Measure preserving automorphism of the backspace. That's the, so this is also, so I showed that this is also Rilke precompact. And he showed here that as a result of this the identification of the Rilke compactification, one can show that this group is minimal or totally minimal. Well, it's simple, so minimality is the same as total minimality here. So totally minimal. And the same is true here. And I also kind of improved his proof by using something which is called enveloping semigroup. And this will arise. This will be a main topic of my talk today. This is all of this is just kind of a preface. And then we showed, we have seen here that this led people in model theory to work on that. So we're talking about Ben Yaakov and Tsankov. We heard about this here. So this went again from, I would say, kind of topological dynamics to and finally maybe the last thing that I'll mention here, although maybe there are others. So the last part, or the last interaction with the model theory arose in this way. So in a paper with Misha Migralishvili, we've shown that for G equals, again, S infinity, we have these equalities. I will explain. So the Hilbert algebra is the same as the Watt algebra, and also the same as uniformly continuous functions on G. All of this algebra coincide. And so this is true for this group, whereas for this other group that I considered there, homeomorphisms of the Cantor set, which is again a closed subgroup of S infinity, and is also Röhlke precompact. Here the situation is very different, and the WAP G is a proper subalgebra of UCG. I will explain. I put here some kind of a list, and I will explain it. Not all of it, but parts of it. But this, as I said, this is just an introduction, so this is highlights of what's going on. Some of it is highlight, will be explained better later on. So as a corollary of this difference between these two groups, one can deduce that. Can you break it a little bit? Sure. So as a result of this distinction between these two groups, one can deduce, I mean, this always comes with a natural structure of a semigroup. Again, this enveloping semigroup will be actually behind the curtains here, and we will see that soon. And in this case, the Gelfand space, say, of this algebra, all of these are C-star algebras, and in this case, it has a very natural structure of semigroup. It extends the group action on which the group is always embedded into all of these Gelfand spaces. And here, the situation is completely different because you don't have the equality, and this mysterious algebra, which we call strongly uniformly continuous, is the key for being a semigroup. And then this kind of arrows goes to model theory, and then we have already seen some hints of this here. So I'll just mention briefly, there are works not published yet, or maybe not even fully prepared by Todor and Itai and Thomas, who all sit here. Ibarluccia. Am I pronouncing it correctly? Okay, so this was the introduction, and now I'm getting in earnest into the subject of my talk. And I'm going to start with topological dynamics. So a dynamical system for me is a pair, a compact Hausdorff space, usually metrizable, and a group G, topological group, and it acts on G. This just means that G is embedded into the group of homeomorphisms of X, the compact space. So this comes with uniformity, and we want so in brief, what we want is that this map is continuous in both variables. That's a dynamical system. It is topologically transitive. If, well, let's assume it's metrizable. There exists X0 such that G X0 is everything. It is minimal if Gx is X for every X in X. Well, I'll just equicontinuous if the action is equicontinuous. Okay, as a whole. A point, okay, almost equicontinuous if there exists dense G delta of equicontinuity points. And you can imagine what this is. It is hereditarily almost equicontinuous if, now there are two kinds of way to inherit or to go to dynamical system once I start with xg. One of them is to take subsets of x, which are closed and invariant. This I will call subsystems. And that's what I need here. And the other one is when I take a factor in the usual sense of categories onto map in this case, which is continuous and intertwines the actions. But the difference between these two turns out to be crucial, because this behaves much nicer than this one. Of course, it's a much stronger property. What did I forget? Weakly almost periodic. So here I will write also almost periodic. Almost periodic means in the sense of Bohr, classical sense. What does it mean? This almost periodic, which is the same for all f in Cx, fg is norm-compact. Pre-compact, of course. In Cx, that's a Banach algebra, and in this Banach algebra, we want the orbit of the function to be pre-compact. Then it's called almost periodic, and this is easily seen to be the same as this other property. And here, I want exactly the same, but for all f, is weakly pre-compact. In this Banach space, we have, of course, these two topologies, and I want it to be pre-compact. And there is a theorem that says that this class of functions, okay, I have to explain something that I will do all the time. So let me just first go over the whole list that I need.
Was a connection with Bezikovich.
Excuse me?
Bezikovich almost periodic function. Is it the same or not?
There are many variations. I'm not sure even what you call Bezikovich. I think it's for the real numbers, some notion. Maybe it's very specific. There are many variations, but these are easily generalized to any group, and these are the ones that I will be interested in. Okay, so what about this remark? I mean, if I have any dynamical system X, I can look at Cx, and I can look at the function in Cx which have one of these various properties. I mean, not all of them were defined for functions, but it turns out that you can do that. And then you get a certain subalgebra, which is closed and invariant. And of course, we have a duality for compact spaces, we can talk about compact spaces, or alternatively, we can talk about commutative sister algebras, and then the Gelfand space is the functor that gives us this duality. A subalgebra goes to its Gelfand space, and for a compact space, which is compact, and for a compact space, I take the functor, which is the sister algebra of all continuous functions. So I can talk dually about properties when I'm talking about functions, or when I'm talking about compact dynamical system. Okay. So the theorem that I was trying to refer before says that that WAP is always hereditarily almost equicontinuous. That's not trivial, and it's an important fact. So whenever I have x, I mean, to sum up here, whenever I have x, I can talk about all this list. There makes sense if instead of putting g, I put there x. And then I get some algebras of x, that is to say factor of x, which will be the largest one, which is hereditarily almost equicontinuous. The largest one that will be WAP. The largest one that will be almost periodic. This is the most well-known one. In ergodic theory, it corresponds to discrete spectrum. This is the analog here. And so on and so forth. And when I take what is called the universal ambit, which is just what? It's that I take right uniformly continuous G, that's an algebra. And that's the largest algebra that interests me. If I take the Gelfand space of this, I get what is called the universal ambit, and this maps onto every topologically transitive. Remember, the point x naught is dense. That's a universal object, and the morphism is unique because here the identity or something like that corresponds to this point. So it's enough to say which point goes to which point. One point, it determines the whole thing. So that's very convenient. And I should have added there to the list this big algebra. Okay, so second part. Do I use this? That's wet, right? So this will make a mess. I want a dry one. Oh, thank you. Thank you. Okay, eraser is nice. So the next thing is enveloping semigroups. What is it? I start with xg, and it gives me a set of functions. Remember, G is an abstract group sitting outside, topological group. So I look at the homeomorphisms, where I consider this as I consider them as elements of the space, say R to the x to the x. Just mapping from x to itself, but with pointwise convergence topology. So that's a compact space by Tikhonov, and I take the closure, and I get a semigroup, which is called the enveloping semigroup of the dynamical system xg. And it has the following properties. So G sits inside, of course, in this way, densely. And it has the property that P goes to let's say Q goes to Q, P is continuous. So with these two properties, I get some kind of abstract object, a compact semigroup in which a group sits densely and where multiplication on the right is continuous. This I call right topological semigroup. Actually, it's called admissible because this extra condition makes it admissible, but let's use this terminology. So the enveloping semigroup has this property. And let me just, to convince you that it is important, let me give you a theorem, multi-theorem. Part 1, xg is, all of this will start like that, equicontinuous, if and only if E is a topological group. That's not strictly true. I need this to be topologically transitive. Second, distal. I didn't define distal. Well, here I said that I already gave two properties. One is equicontinuity. The other one was this bow, almost periodicity. A third one will be, if we are in a metric case, there exists an invariant metric, which is compatible with the topology. So when I have an isometry, then I have, of course, this property for every x, y, and g. And of course, I start with my space. I start with 2 points, x, y. I can never bring them together closer than they are if I adopt this kind of metric, okay? But for a while, people thought that if you have something minimal and you have this property that you cannot bring these two together, this is called distality, then this will imply equicontinuity, but that's wrong. And there were examples given in the early 60s by Furstenberg and others that showed that that's not the case. And this gives us a new class, distal, which I haven't put there, but I defined it for you right now. If and only if E is a group, just algebraically, no topology. If it's actually a group, that makes it distal. 3, drop. If and only if E comprises continuous functions from x to x. And this is essentially Grothendieck's theorem. You can show that it's equivalent to it. 4, here is the HAE. If and only if E is metrizable. And one can add more, but metrizable. Yeah. Well, usually that's very big. I mean, if we start with Z, the integers as a discrete group, and we take the universal orbit, so L infinity now, that's the same as what I called before, right? Uniformly continuous Z. Of course, there's no uniform, nothing here happens. It's topological, it's discrete. So this is beta Z, the Stonechek compactification. The Gelfand space is Stonechek compactification, so it's huge. And this is kind of you can show that this is the enveloping semigroup of the Bernoulli. This is an example. If you start with 0, 1 to the z, you take shift, and you take the enveloping semigroup. This is just beta t, beta z. So usually it's big. If it's metrizable, then it's HAE, and that's if and only if. That's what is separability? What do you mean this is separability? It's always separable. If my group is countable, in the sense the topologists use, I mean, they say second countable, and they say separable. Right, right. So it is separable in the sense that there is a dense countable set, but it's far from being metrizable. Like beta z. Beta z is also separable. It has z sitting inside. Is it then? Right. 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 Okay. There will be no confusion. Countable base. Yeah. Okay. So. Okay, so let me give you an example. One I gave you already. Okay, and let me give you another one, which is more in the spirit of this conference. So let S infinity act. So this is OG on N union infinity, a one-point compactification, call it X, compact space, and it acts just by permutation on N, and it fixes infinity. Obviously, there is no other way. And I'll give you a description of the enveloping semigroup of this system, which is very easy to describe. Very easy to describe as follows. I'm given an injection. A is an infinite subset of N, and this is an injection. And then I define an element P alpha of J. It equals to alpha of J in the case where J is in A and infinity otherwise. That's well defined. Obviously, it's a continuous thing. And you can easily show that the set of all is exactly this dynamical system or semigroup. Okay? Since every element here is continuous, we can apply this theorem and deduce that this is a WAP system.
What's the action?
Here you have S infinity sitting inside, and it's you compose. These are maps.
But you start from what X?
This is my X. Where did I write it? Here. That's the continuation of that. I take one-point compactification. That's the example that I'm showing. I'm starting with a one-point compactification, and I'm identifying.
What is the variable there? You are varying over all A and all alpha.
For all infinite A inside N. No, I let them all alpha, all possible alphas. All A varies, of course. Everything varies. All injections. No, all domains, all possible domains, which are always infinite.
Partial injections from
Partial injections, right? And that's corollary. This system is what? But you see, the way you get the enveloping semigroup, you can immediately see that if you take any number of, no star here, so I'm using an old notation. The enveloping semigroup of this is again the same thing. You don't change anything if you take products. So from this and some other little arguments, which are very easy, you can actually see, you can get the following corollary that pardon? Corollary is that for S infinity, we have WAP is the same as uniformly continuous. Just from that. And I think that one may try to push this example much further and prove. Yeah, Polish groups, the Polish group. Pointwise uniform, pointwise convergence. So let me just mention two theorems, and if I'm not quoting them correctly, please. One is Ben Yaakov and Tsankov in this connection, because I mentioned that. So for Rilke precompact G, WAP is equal to UCG if and only if, now I'm saying things that I'm not so comfortable with. G is the automorphism group of M for M, a stable Aleph not categorical metric structure. Is that a correct theorem? I'm waiting for some people in the audience to give me the okay. And, well, that's the proof. That's not the theorem. Proof Grothendieck. And the second one is Ibarluccia. And this says that WAP G is the same as HAE. G is the same as strongly uniformly continuous G for every Rilke precompact G. So again, the topological dynamics gives us some kind of nice, very nice, elegant theorems in. I wanted to give you a proof of the main lemma that makes the enveloping semigroup so powerful. And the lemma says, I'll not do it because then I'll not be able to do what I want I won't achieve my goal by showing you what something. But the lemma I will state, if E is a right topological semigroup, you don't even need admissibility or anything, then there exists an element which is an idempotent. The proof is just 2 lines, but I'll skip it. But this theorem, which is just Zoran's lemma, that's the proof, like Grothendieck was before, is so powerful that, I mean, it pops up in many things. And if I have an opportunity, I'll talk here about the theorem of Kra and Bernard, Horst Kra and Alejandro Mas. And I'll show the connection there. And there again, this lemma is crucial. And you can get a very short proof. Pardon?
I'm not sure exactly what's wrong.
Well, I define this to be a compact semigroup. Compact, of course. Compactness is very crucial.
So there's no any connection. Simply just a general.
No, I haven't used it. Well, it's used in this theorem somewhere, but idempotent. E squared is equal to E.
So each compact semigroup is one?
Wait a minute.
Each compact semigroup has idempotent.
Right topological semigroup.
Right.
Because that's very important. I mean, it's a minimal condition. You only want multiplication of the right to be continuous, and that's sufficient. What is the question, Itai? That's an easy question. Okay. Now, yes.
In general, this is not inverse. Not.
That's just what I've told you, and I said the proof is very, very trivial. It's just
In that case, it's not inverse because sometimes
it's not invertible.
inverse semigroup.
No. I'm not assuming anything beyond what I said.
For unitary group, this is inverse.
Okay. And now we come into the main topic of the talk. Very late, I guess. And that's the tame, the notion of tameness. What is tame? So here I'm citing a theorem. It's a kind of a dynamical version of the famous theorem of Bourgain, Fremlin, and Talleyrand. Dichotomy. And it says the following thing. Let xg be a metric dynamical system. Then we have a dichotomy. Either that's the first possibility. Ex is Fréchet, meaning this is a general topological definition. I have a subset A sitting in my X, and I take not X in abstract space, right? Y. And it's in the closure. Then there exists an in A, which a sequence which converges to X. A sequence, that's the main point, of course. Sequence. The topology is given by convergent sequences. Or Ex is a wild space and it contains a copy of beta n. Of course, no convergent sequences there. Yes?
Can you see more than just when this copy of beta n? Can you show the dynamical version of this second?
Okay, let's talk about it later, because I really want to say something
X
that...
is a metric space, compact metric space.
Yes. But Ex, that's a different object, much bigger. Okay. This is if and only if Ex comprises bear one functions. Bear one functions. Continuous limit of a sequence of continuous functions. So this is important. And now a new subject. Sorry. This new subject is hierarchy of Banach spaces. So a Banach space can be complicated geometrically. It can be less complicated geometrically. And this is kind of an analogy to what happens there. We have Hilbert spaces. They are maybe the best, nicest one. I mean, we're talking about infinite dimensional Hilbert. Then we have reflexive. Then we have Asplund. Here is the definition. So V is my Banach space, always. And for every U, maybe not such a good name, a subspace U is separable. Separable Banach space, that's the definition of Asplund.
For every U separate.
Pardon?
For every U separate. For every U separate.
Sorry. Yeah, of course, if V is separable, then it's not necessary, but if, yeah. So we see, of course, that this is true. And then the next stage is what we call Rosenthal. For some strange reason, Rosenthal. For some strange reasons, this wasn't given a name. And the definition is V does not contain a copy of L1, little L1. Does not contain isomorphic copy of L1. So people for decades were saying a Banach space that does not contain L1 isomorphically, not isometrically. No. No, it's also not isometrically. Yeah. So we called it Misha Migralishvili, and I called it Rosenthal spaces, and I think that's completely justified. Okay. So what's the connection? Suppose I have XG, a dynamical system, and I have H, which maps G into V, that's a Banach space. Into L of V, operators on the Banach space, bounded operator on the Banach space, and no, I want isometry. Sorry. And this is for technical reason, you will see immediately why, it's a cohomomorphism. Cohomomorphism. And I have alpha, which maps X into the dual unit ball.
What does it mean?
Homomorphism of groups. Well, I want the adjoint to be a homomorphism. So this, because that's really what interests me. And this I want to be continuous. And continuous with respect to the weak star topology. When I can do that, and I can make alpha a homeomorphism, one-to-one, remember we are dealing with compact spaces, so that's all I need. Continuous one-to-one. Then I say that this dynamical system is representable on V. And if I have a class of Banach spaces, like one of these, then I say it is Hilbert representable, Hilbert reflexive, etc., etc. Every space, of course, trivially can be represented always on Cx by just taking a point and sending it to the so this is an obvious thing to do, but it's bad because geometrically this space is bad. So now we can ask which dynamical system can be mapped into which classes of here is a theorem. theorem. Again, xg, a metric dynamical system. X is what? If and only if this is a theorem of Migrelishvili, it is representable on a reflexive Banach space. 2. X is hereditarily almost equicontinuous if and only if Asplund. This is Uspensky, Migrelishvili, and myself. And the last one is X is tame if and only if wasn't. And I have with Benji Weiss some theorem about.
What does it take?
Sorry. So I omitted the definition of tame right after the dichotomy theorem. I should have said that the dynamical system is called tame if it falls into the nice department. If it behaves, if its enveloping semigroup consists of bare one functions or it's a Frechet space, then it's called tame. I said the other case is untame, is wild, and I implied perhaps that this should be tame. Okay. Yes, very subtle. This is, of course, an excuse, an afterthought. So that's what I'm going to say. I was going to say. There is a theorem about Hilbert. I will not state it because it's not as nice. This belongs to Benji and myself. Essentially, it says what we can say is that if there is an open question there. I don't have the time to explain, but what we showed, Benji and I, is that if you take a dynamical system x mod, it's pointed, so that means this has a dense orbit. Then it is Hilbert representable if and only if there is a function f which is in this space Bg, here it appears. Bg is classically the space of, well, let's say it's positive definite. To be precise, it's positive definite, and if I take its orbit closure in the space of functions from my group to R, then this is just the same thing with f as the point. So this is a pointed isomorphism. So positive definite or Fourier transforms, the algebra generated by Fourier transform closure, that's the algebra of Hilbert. But it's a bit more subtle. Okay. Now I have what? I have 5 minutes, say, this will have to do. There was in the 70s, a very famous question that was, at that time, the geometry of Banach spaces, infinite dimensional Banach spaces, of course, was very popular. Today, it's less in vogue because people are more interested in finite dimensional spaces and how they can be embedded into each other, etc. And the question was, the question was whether there exists in this hierarchy of Banach spaces is what was it, reflexive and Asplund. Asplund. The question was this, whether it's equal or not. It was open for a long time, and then in the 70s, James, and independently, Lindenstrauss, Joram Lindenstrauss. Nowadays, you have to say Joram Lindenstrauss. Okay, at the same time. Produced counterexamples. Okay? Now I want to show you that this can be done very easily using this kind of apparatus. Why? So in topological dynamics, it is rather easy to produce examples of even subshifts. What is a subshift? A subshift is this Bernoulli dynamical system. G, this is the space, contour space. G acts by permutation on itself, and it gives me a dynamical system. And anything in here, which is a subsystem, remember I defined that, is a subshift. Okay? So there are subshifts which are what? Tame, but not. I'm sorry. I'm sorry. No. I'm sorry. I asked the wrong question. Asplund, but not Rosenthal. I'm sorry. Yeah, this is easy. This is the hard one. I just got confused. So this was the open question. Okay, and that's what I want. So I want it to be tame, but not HAE. So this is easy to produce. Why? One reason, one way to see it is we have, again with Migrelishvili, we have a theorem that says that a subshift is HAE if and only if it's countable. So these are the HAE subshifts are exactly the countable ones. And we have also a condition for tameness, and you can use this to produce examples like that. And then just use the theorem. What did the theorem of representation said? It said if you have a dynamical system like that, you can represent it because it is tame, you can represent it on a Rosenthal space. But this theorem goes both ways. So if it would have been HAE, that would mean that, so I cannot, because it goes if and only if I get an example just by finding in this category of dynamical system, I find such an object, it gives me immediately one like that.
It's the same example.
Pardon? There are many examples like that. You know what a Sturmian dynamical system is? Yeah. You take the circle, you split it into two parts, right and left, and you take an orbit, rotation by alpha, and you get a symbolic flow. It's 0 here, it's 1 here. You get the name function. This is an example.
Example of James Osaka.
Oh, no. The disadvantage of this method is I have no slightest idea what the Banach space is. It's just, this is just a game in that sense. I don't know anything about that.
This means you're telling us something about the proof of the theorem then, because...
Exactly. Of course, everything, you can go back to the proof, trace the proof, try to build the Banach space like that, but it's very far from that. I mean, all we are saying is there exist. That's all. Exist. And let me finish 1 minute. So let me finish with a question and a suggestion. There is a very interesting family of Banach spaces called K-convex spaces. I don't have the time to define them even, but they sit kind of in between. Let me just draw a little diagram. I have it here. Where is the diagram? Here. Here is the diagram. So this is Hilbert. This is reflexive. This is Asplund. And this is Rosenthal. And the K convex sit here somewhere. Whoop. No, it doesn't even coincide with reflexive. So this is K convex. This is K convex. And as far as I know, Stevo thinks maybe differently, but I asked Vitaly Milman, and there was a conference in Toronto 3 years ago. Nobody of the experts knew the answer, whether there is something which is here and not here. Okay? And again, in topological dynamics, there is a very easy criterion for deciding when a subshift is here. It's countable. And I propose a certain class of dynamical system which, in the same spirit, would correspond to this K convexity. And this is what is called null. And it is defined by means of entropy, topological entropy, so sequential topological. I will not give the exact definition. And I propose to prove a theorem like that. I doubt whether it's true, but I was thinking about it for a long time and couldn't make a great progress, only small ones. But if I can show that null corresponds to K convex in the same way as these other pairs, then there are ready examples of dynamical systems which are not countable, hence not in here. But on the other hand, they are null. So this will give a counterexample to the Banach space. And I'm 1 minute late, so I'm sorry. That's the conjecture. I don't know to prove either way. And I need both, right? A bit, yes. I was very enthusiastic about that when I learned about the K convexity. This was in Toronto, 3 years ago? And I sat in the same office with my friend Gidon Shechtman. We talked about it. And at the beginning, I was very enthusiastic. Now I'm a bit skeptical. Yes?
Regarding this Asplund strictly containing Rosenthal, well, I think that what we know today is a very quick answer. Okay, so there's another result of Thomas Valentia that you didn't mention, which is that basically is a way that...
I didn't mention it because I didn't know what NIP is. Right.
So only to show that there is an Aleph not categorical structure that's neat and not stable. For example, Q order.
Wait a minute. Because
you take G equals the automorphism group of Q with the order.
But you're using the fact that Asplund is the same as WAP for these groups. Yeah. In this context, right? Absolutely. That will do it again. Yes.
Thanks. We'll wait until 2:15.
So anyway, we must reserve maybe, I don't know, Saturdays, much more time than I